Somewhere, something incredible is waiting to be known. Carl Sagan. For centuries, humanity has looked to the stars in search of answers to our deepest questions, but each discovery reveals even greater mysteries. From the mind-bending physics of black holes to the possibility of ancient alien visitors, our universe is filled with enigmas that challenge our understanding of reality. Join us as we explore the most astonishing mysteries of the universe. When information, matter, or energy falls into a black hole, we encounter one of modern physics' most intriguing paradoxes. Imagine a particle carrying detailed information about its properties, such as position and speed. As this particle crosses the event horizon, the boundary beyond which nothing can escape, that information seems to vanish from our observable universe. This scenario raises fundamental questions because the laws of quantum mechanics state that information should never be lost. The apparent destruction of information in black holes challenges our understanding of the fundamental nature of reality and the interplay between gravity and quantum mechanics. This contradiction between quantum mechanics and general relativity is known as the information paradox. Stephen Hawking once proposed that information falling into a black hole could be lost forever. But this idea contradicts the principle of quantum determinism, which states that the past and future states of a system should always be determinable from its present state. Recent theories, including developments in string theory and the holographic principle, suggest that information might be preserved in some way. One idea is that information is encoded on the event horizon itself, much like a hologram, preserving the details without actually losing them inside the black hole. Another fascinating notion is the concept of Hawking radiation, where black holes emit radiation over time and eventually evaporate. Some scientists theorize that information might slowly leak out through this radiation, albeit in a highly scrambled form. This complex interplay between quantum mechanics and general relativity remains one of the deepest mysteries in physics, fueling ongoing research and debate. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, are enigmatic giants residing at the centers of most galaxies. Their formation is still a topic of active research, blending several fascinating theories into a compelling narrative. One prevailing hypothesis posits that these colossal black holes started as smaller intermediate mass black holes. Over cosmic timescales, they grew by voraciously consuming gas, dust, and even entire stars from their surroundings. This accretion process, combined with mergers between black holes, steadily built up their massive sizes. Imagine an insatiable cosmic entity continuously feasting on anything within its gravitational pull. Another theory suggests that the seeds of supermassive black holes may have formed very early in the universe's history, just a few 100 million years after the Big Bang. In these primordial conditions, giant clouds of gas could have collapsed directly into large black holes, bypassing the usual stellar-sized black hole phase. This process, often referred to as direct collapse, might explain how supermassive black holes appeared so early in the universe. Galaxy mergers also play a significant role in the growth of these black holes. When two galaxies collide, their central black holes can eventually merge, forming an even more massive black hole. The merging of these galaxies often drives large amounts of gas toward the center, providing additional fuel for the black hole to grow rapidly. Across billions of years, these Goliaths of gravity sculpt the galaxies around them, influencing star formation and the dynamics of galactic cores. Understanding their formation not only unravels the mysteries of these cosmic titans, but also provides critical insights into the evolution and structure of the universe. Hawking radiation, proposed by physicist Stephen Hawking in the 1970s, is a groundbreaking concept that combines principles of quantum mechanics with general relativity to explain a previously unimagined phenomenon. Black holes can emit radiation and over exceedingly long timescales gradually evaporate. Near the event horizon of a black hole, the boundary beyond which nothing can escape, quantum mechanical effects come into play. According to quantum theory, particle-antiparticle pairs are constantly being created and annihilated throughout space, even in the vacuum around a black hole. Occasionally, these pairs form right at the event horizon. In some instances, Due to the intense gravitational forces, one of these particles may fall into the black hole while the other escapes into space. The particle that escapes carries away some energy from the black hole, effectively reducing the black hole's mass. This escaping particle is what we detect as Hawking radiation. Over incredibly long periods, this process causes the black hole to lose mass and energy. As it continues to emit Hawking radiation, it gradually shrinks, a process referred to as black hole evaporation. The full evaporation of a black hole is a slow process for most black holes, especially the supermassive ones. This occurs over time scales far beyond the current age of the universe. However, for small black holes, the loss of mass can speed up dramatically as they get smaller, leading to a final burst of radiation before they vanish entirely. Hawking radiation not only provides a mechanism for black hole evaporation, but also bridges the gap between quantum mechanics and Einstein's theory of general relativity. It serves as a step towards understanding the deeper connections between the laws governing the tiniest particles and the largest structures in the cosmos. The idea of harnessing energy from rotating black holes is not merely the stuff of science fiction, but is grounded in fascinating theoretical physics. Rotating black holes, also known as Kerr black holes, possess an enormous amount of angular momentum and gravitational energy. This seeming paradox of tapping into a black hole's immense power was first proposed by physicist Roger Penrose in the form of the Penrose process. The Penrose process involves a particle entering the ergosphere, a region just outside the event horizon of a rotating black hole where space-time is dragged around at astonishing speeds. Within the ergosphere, it is theoretically possible to split the particle into two. One part falls into the black hole while the other escapes, carrying off more energy than the original particle had. In doing so, the process extracts a fraction of the black hole's rotational energy. Another fascinating concept is the Blandford-Znajek process. This theory suggests that magnetic fields surrounding a black hole could interact with its rotation, channeling energy out in the form of powerful electromagnetic radiation. Jets of high-energy particles, often observed emanating from the regions around supermassive black holes at the centers of galaxies, could be an indication of such energy extraction mechanisms at work. These theoretical methods present tantalizing possibilities, but come with immense practical challenges. The extreme conditions and immense scales involved make actual energy extraction a daunting, if not currently impossible, engineering feat. Nonetheless, studying these processes enriches our understanding of black hole physics and the incredible forces at play at the edges of our scientific comprehension. While we may be far from building black hole power plants, these ideas stretch the boundaries of what we consider possible, propelling us toward deeper inquiries into the universe as most enigmatic entities. Whether or not we can ever directly harness this energy, the principles behind these processes continue to offer profound insights into the nature of space-time and gravity. Should you find yourself falling into a black hole, your experience would depend greatly on the black hole's size and mass. For a stellar mass black hole, typically several times the mass of our Sun, the journey would be extraordinarily violent and brief. However, falling into a supermassive black hole, millions or billions of times the mass of the Sun, could provide a longer, though equally unsettling trip. As you approach the event horizon, the point of no return, the effects of gravity become extreme. For a stellar mass black hole, tidal forces' extreme differences in gravitational pull would stretch and compress your body in a process whimsically called spaghettification. You would be elongated along the direction of the black hole's pull while being compressed along the other directions, quickly leading to your demise before you even reach the event horizon. In contrast, if you fell into a supermassive black hole, the longer distance to the singularity at its core means tidal forces at the event horizon would be less intense. You could theoretically pass the event horizon without immediate catastrophic spaghettification. As you fall deeper into the black hole, the view to the outside universe would shrink to a small bright spot directly overhead, slowly fading as you approach the singularity where gravity crushes all matter to an infinitely small point. Once inside the event horizon, the laws of physics as we understand them break down. Theories suggest time and space become interchangeable, leading to speculations about what might occur. Some suggest you could encounter the singularity where matter is crushed to an infinitely dense point, ending your journey. Others hypothesize the possibility of reaching a region where space-time could connect to another part of the universe through hypothetical constructs called wormholes or Einstein-Rosen bridges. Whether the final moments involve a rendezvous with a singularity or passage through exotic cosmic pathways, falling into a black hole remains a mysterious and perilously final voyage, an exploration on the very edge of our scientific understanding. Detecting exoplanets, the planets that orbit stars beyond our solar system, involves several ingenious methods, each leveraging different aspects of astronomy to unveil these hidden worlds. One of the most successful and widely used techniques is the transit method. When an exoplanet passes directly between its parent star and us, it causes a slight periodic dimming of the star S-light. By carefully monitoring and measuring these dips in brightness, astronomers can infer the presence of an exoplanet, its size, and even some clues about its atmosphere. Another powerful method is the radial velocity or Doppler technique. This approach relies on detecting tiny wobbles in a star S position caused by the gravitational pull of an orbiting exoplanet. As the planet orbits, it tugs on the star, causing it to move slightly towards and away from us. This motion shifts the star S light spectrum towards the blue end when it moves towards us and towards the red end when it moves away. By studying these spectral shifts, scientists can estimate the exoplanet S mass and its orbital period. The direct imaging method, though challenging, involves capturing actual images of exoplanets by blocking out the overwhelming glare of their parent stars. Using advanced instruments and techniques like coronagraphs or star shades, astronomers can isolate the faint light reflected or emitted by the exoplanet. This method is particularly useful for studying larger exoplanets that are relatively far from their stars, in regions where the contrast between the planet and starlight is less blinding. Another intriguing approach is gravitational microlensing, which takes advantage of the warping of space-time caused by a massive object, such as a star or planet, passing in front of a more distant star. The gravity of the intervening object acts like a lens, magnifying the background star S light in a specific pattern. If an exoplanet is part of the intervening system, its presence can be inferred from the distinct characteristics of the light curve. These methods, often used in combination, have led to the discovery of thousands of exoplanets, painting a diverse and fascinating picture of planetary systems far beyond our own. With each detection, our understanding of the universe expands, revealing the potential for worlds that might harbor life or offer conditions vastly different from those we know. Super-Earths are a class of exoplanets with masses larger than Earth S, but significantly less than those of ice giants like Uranus and Neptune. Typically, super-Earths boast masses ranging from about 1 to 10 times that of Earth. Their unique position in the planetary spectrum has captivated scientists as they offer a window into diverse planetary formation and compositions. One reason super-Earths intrigue scientists is their potential similarity to Earth, which raises questions about their habitability. Many super-Earths lie within their star's habitable zones, the region where conditions might allow for liquid water to exist on the planet S surface. Water is a key ingredient for life as we know it, making these planets prime candidates in the search for extraterrestrial life. The composition of super-Earths can vary widely, from rocky planets with thin atmospheres to water worlds with deep global oceans. Studying super-Earths also broadens our understanding of planetary formation. Our solar system lacks planets with masses between Earth and Neptune, so discovering and studying super-Earths in other systems helps fill in gaps in our knowledge. These planets might represent a common step in planetary evolution, providing clues on why certain planetary systems evolve differently. Some super-Earths have intriguing atmospheric compositions, detected by analyzing the starlight that filters through their atmospheres during transits. This spectroscopy can reveal the presence of gases like hydrogen, helium, and potentially even more complex molecules. By studying these atmospheres, scientists hope to learn about the processes shaping these worlds, including volcanic activity, weather patterns, and potential biosignatures. Super-Earths embody a diverse array of worlds, each with the potential to challenge and expand our definitions of habitability and planetary formation. As our detection methods and technologies improve, the study of these planets will undoubtedly yield more surprises, deepening our understanding of the myriad possibilities within our universe. Rogue planets, or nomadic planets, wander through the galaxy unbound by any star. These mysterious worlds, existing in the dark expanse between stars, raise fascinating questions about the potential for life in such isolated environments. While the absence of a parent star presents significant challenges for sustaining life as we know it, certain theoretical scenarios suggest it might not be entirely out of the question. First, let us consider the possibility of subsurface oceans. If a rogue planet retains enough internal heat from its formation or experiences tidal heating from interactions with a large moon, it might possess a subsurface ocean insulated by a thick layer of ice, similar to the icy moons of Jupiter and Saturn in our solar system. Such oceans could potentially harbor microbial life or even more complex organisms, exploiting the energy from hydrothermal vents at the ocean floor. Another intriguing scenario involves thick atmospheres. If a rogue planet has a dense atmosphere rich in hydrogen or other insulating gases, it could trap enough heat to maintain liquid water on its surface or beneath a layer of ice. This atmospheric blanket would act like a giant thermos, retaining geothermal heat and potentially providing conditions suitable for life. This concept of atmospheric insulation expands the possible habitable zones far beyond the confines of starlight. Life may also arise from different biological principles than those on Earth. In the absence of sunlight, alternative energy sources such as chemical energy from the planet's interior might serve as the basis for an entirely different kind of biosphere. Extremophiles on Earth microorganisms that thrive in harsh environments like deep-sea vents and acidic hot springs hint at life's remarkable adaptability to diverse energy sources and conditions. Rogue planets push the boundaries of our understanding of habitability and challenge our perceptions of where life could exist. While the conditions are undoubtedly extreme, the resilience of life on Earth in similarly harsh environments suggests that life on rogue planets, though speculative, remains a tantalizing possibility. As our knowledge and detection techniques advance, these lonely wanderers might one day reveal themselves as harboring the secret to life's adaptability beyond the stellar neighborhoods we are accustomed to. Searching for biosignatures on exoplanets involves using sophisticated techniques and instruments to detect chemical and physical signs of life from light years away. These biosignatures are essentially the indicators of biological processes that can be observed and measured from Earth or orbiting space telescopes. The quest for these telltale signs is one of the most exciting frontiers in modern astronomy and astrobiology. One primary method is the analysis of exoplanetary atmospheres, which can be done during transits when an exoplanet passes in front of its host star. A small fraction of the star's light filters through the planet's atmosphere. By examining this light with tools like spectrometers, scientists can identify the absorption lines corresponding to specific gases. Certain gases, such as oxygen, methane, or ozone in particular concentrations, might indicate biological activity. For instance, on Earth, a combination of oxygen and methane in the atmosphere is mostly produced by life. Another approach involves the study of reflected light from an exoplanet known as direct imaging. Instruments use advanced techniques to block the overwhelming light from the parent star, allowing astronomers to analyze the spectrum of light directly reflected off the planet's surface or atmosphere. Reflected light can reveal various surface materials and atmospheric components. Detection of unusual surface compositions, like chlorophyll-like signatures associated with photosynthesis on Earth, might provide clues about potential life. Additionally, scientists consider the possibility of detecting technosignatures, which are signs of advanced technology. These might include unusually structured light patterns or radio signals akin to those our technology emits. Though the search for technosignatures is more speculative and challenging, the potential discovery of such signals would be a groundbreaking indication of intelligent life elsewhere. Groundbreaking missions like the Kepler Space Telescope and the James Webb Space Telescope, along with upcoming projects, utilize these methods to systematically explore exoplanets' atmospheres and surfaces. As our technological capabilities grow, so does our ability to detect subtle signs of life, pushing us ever closer to answering the age-old question, are we alone in the universe? With each advancement, the dream of discovering life beyond Earth moves from the realm of speculation to the cusp of scientific reality, making the search for biosignatures an exhilarating journey into the unknown. The Fermi paradox is a fascinating puzzle named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This question encapsulates the seeming contradiction between the high probability of extraterrestrial civilizations existing elsewhere in the Milky Way galaxy and the lack of evidence or contact with such civilizations. Given the vast number of stars and potentially habitable planets, Fermi's simple yet profound query continues to perplex scientists and stimulate intriguing hypotheses. One of the central tenets of Fermi's paradox lies in the Drake equation, which estimates the number of active, communicative extraterrestrial civilizations in our galaxy. Factors such as the vast number of stars, many of which have planets in habitable zones, suggest that statistically, intelligent life should be relatively common. Our Milky Way alone contains around 100 billion stars, many of which are orbited by planets that could host life. Yet, despite the seemingly favorable conditions, we have no conclusive evidence of extraterrestrial civilizations. Several theories attempt to explain this paradox. One idea is the possibility of the Great Filter, a hypothetical stage in the evolution of life that is extremely unlikely or difficult to overcome. This filter could be behind us, meaning life rarely evolves to complex organisms or ahead, suggesting advanced civilizations self-destruct before achieving interstellar communication. Either scenario presents sobering implications for our own civilization's future. Another hypothesis is the concept of the zoo hypothesis, where advanced extraterrestrial civilizations deliberately avoid contact with us, observing humanity from afar like animals in a zoo. They might be waiting for us to reach a certain level of technological or ethical maturity before making contact. Others propose that interstellar travel or communication might be inherently difficult or resource-intensive, limiting the spread or detectability of advanced civilizations. Additionally, some suggest that we might not be recognizing the evidence of extraterrestrial life because it differs significantly from our expectations. Life forms might be so alien in form and function that we fail to perceive their presence. The Fermi paradox remains a profound and open-ended question, driving both scientific inquiry and speculative thought. Each proposed solution, whether it leans towards biological, technological, or sociological explanations, brings us closer to understanding our place in the cosmos and the potential for others sharing it with us. The Great Attractor is a gravitational anomaly in intergalactic space that exerts a powerful pull on the galaxies in its vicinity, including our own Milky Way. Located roughly 150 to 250 million light-years away in the direction of the constellation Centaurus, this mysterious region is part of what is known as the Laniakea supercluster, a massive collection of over 100,000 galaxies bound together by gravity. The intrigue surrounding the Great Attractor arises from its immense gravitational influence. This gravity well is drawing galaxies towards it at velocities of up to several hundred kilometers per second. Observations indicate that entire clusters of galaxies are being pulled towards this enigmatic point. Even our local group of galaxies, which includes the Milky Way, is moving towards the Great Attractor at approximately 600 kilometers per second. Determining precisely what constitutes the Great Attractor is challenging because it lies within the zone of avoidance, an area of the sky obscured by the dense plane of our Milky Way galaxy, filled with stars, dust, and gas. This obscuration makes direct observation difficult. However, advanced observational techniques and the use of X-ray astronomy have allowed astronomers to partially peer through this dense foreground. Research suggests that the Great Attractor is likely a major supercluster structure with large concentrations of galaxies, dark matter, and hot gas contributing to its intense gravitational field. One key structure associated with the Great Attractor is the Norma cluster, a massive cluster of galaxies situated near the center of this gravitational anomaly. Nonetheless, the full extent of what comprises the Great Attractor remains an active area of research. Understanding the Great Attractor not only helps us comprehend the motion of galaxies within our local cosmic neighborhood, but also provides insight into the large-scale structure of the universe. This region of space exemplifies the complex gravitational interactions that shape the cosmos, influencing the movement and distribution of galaxies across vast distances. Cosmic voids are vast, relatively empty regions in the universe, devoid of much of the matter that makes up galaxies, stars, and other celestial structures. These voids, some spanning hundreds of millions of light-years across, form an integral part of the large-scale structure of the universe, often described as a cosmic web of filaments and clusters with the voids as the spacious gaps in between. The formation of cosmic voids is closely tied to the evolution of the universe itself. Following the Big Bang, the universe was initially a nearly uniform soup of particles and energy. Over time, slight quantum fluctuations in this primordial matter density grew due to gravitational attraction. Regions with slightly higher densities attracted more matter, forming galaxies and clusters. Meanwhile, less dense regions lost their matter to these denser regions, expanding into the vast voids we observe today. This process, governed by gravity and the expansion of the universe, has been ongoing for billions of years. Inside these cosmic voids, things are not entirely empty. Instead, they contain very low-density gas, some dark matter, and a sparse population of galaxies and galaxy clusters. The average density of galaxies in these voids is significantly lower than in the more densely populated filamentary structures. The galaxies found within voids tend to be smaller, less luminous, and often isolated compared to those in richer regions of the cosmic web. Understanding cosmic voids not only sheds light on the distribution of matter in the universe, but also provides valuable insights into the fundamental processes driving cosmic evolution and the large-scale dynamics of the cosmos. The conditions within cosmic voids lead to unique evolutionary paths for galaxies, making these regions fascinating subjects for studying galaxy formation and evolution distinct from denser cosmic areas. Moreover, cosmic voids offer unique opportunities to study dark energy, the mysterious force driving the accelerated expansion of the universe. These voids, being underdense regions, react more sensitively to dark energy, making them excellent natural laboratories for probing its properties. Although seemingly empty, cosmic voids are rich in information about the universe's formation, the distribution of galaxies, and the enigmatic nature of dark energy. Their study continues to deepen our understanding of the universe's large-scale structure and the forces shaping its evolution. Galaxy filaments are colossal thread-like structures composed of galaxies, gas, and dark matter, forming the backbone of the universe's large-scale structure. These filaments can extend across hundreds of millions of light-years, connecting clusters and superclusters of galaxies into a vast, intricate cosmic web. They are among the largest known structures in the universe and play a fundamental role in its overall architecture. The formation of galaxy filaments began soon after the Big Bang, when slight density fluctuations in the primordial matter distribution acted under gravity's influence, pulling matter together into increasingly complex structures. As gravity continued to pull matter into denser regions, long, thin filaments emerged, linking galaxy clusters and sprawling across the cosmos. Dark matter, though invisible, constitutes the scaffolding around which ordinary visible matter congregates within these filaments. Galaxies follow the dense trails created by dark matter, driven by gravitational forces that funnel matter toward dense nodes where galaxy clusters reside. These nodes can merge to form even larger structures known as superclusters. Interactions within filaments play a critical role in the evolution and formation of galaxies, inducing galaxy mergers and triggering new waves of star formation. Studying galaxy filaments provides essential insights into understanding the large-scale structure of the universe and its composition. By mapping these filaments, astronomers can trace the distribution of dark matter whose gravitational influence shapes these cosmic strands. Examining the properties and dynamics of galaxies within filaments helps scientists explore galactic evolution within different cosmic environments. Galaxy filaments illustrate how cosmic forces orchestrate the distribution of matter on grand scales, leading to the rich tapestry of galaxy clusters, superclusters, and voids that define our cosmos. These filaments reveal the intricate dance of matter and gravity that continues to shape the cosmic landscape. Galactic superclusters are among the most massive and monumental structures in the universe, comprising tens of thousands of galaxies stretched across hundreds of millions of light-years. Their formation and evolution are a testament to gravity's power over grand cosmic timescales, from the earliest moments following the Big Bang to the present day. The journey of supercluster formation begins with tiny density fluctuations in the primordial matter distribution of the early universe. These fluctuations, remnants of quantum variances from the earliest moments of the Big Bang, were slightly denser regions of matter spread throughout the otherwise uniform universe. Under gravity's influence, these denser regions began to attract more matter, slowly evolving into larger structures over billions of years. As these structures grew, they formed dense knots of matter known as galaxy clusters, interconnected by somewhat less dense thread-like structures called galaxy filaments. Clusters and filaments subjected to the persistent gravitational pull of these dense regions first formed groups and then larger associations. Over time, multiple clusters merged into more significant formations, resulting in the extensive superclusters we observe today. The evolution of galactic superclusters involves complex dynamic processes. Galaxy clusters within superclusters continue to move under mutual gravitational attraction, occasionally colliding and merging to form even more massive and denser clusters. These interactions can spur new waves of star formation, alter the shapes and properties of galaxies, and drive the growth of supermassive black holes at the centers of galaxies. The ongoing expansion of the universe influences the evolution of superclusters, with some structures becoming more isolated as the space between them stretches. Today, we map these vast structures using tools like large-scale galaxy surveys, providing a 3D view of the universe and revealing the intricate web of clusters, filaments, and voids. Superclusters like the Virgo supercluster, which includes our own Milky Way, and the massive Laniakea supercluster highlight the grand scale of cosmic architecture. The study of superclusters deepens our understanding of the universe's large-scale structure and provides crucial insights into the interplay of dark matter and dark energy in shaping cosmic evolution. By observing these colossal structures, we gather valuable clues about the nature of the universe itself, from its genesis to its ultimate fate. Dark flow is a mysterious phenomenon observed in the large-scale motion of galaxy clusters. Despite the general agreement that the universe's expansion should be uniform, some galaxy clusters appear to be moving in a specific coherent direction, different from the expected pattern. This movement is not accounted for by the standard cosmological model, which includes dark energy and dark matter to explain the universe as observed behavior comprehensively. Scientists first noticed dark flow when studying the cosmic microwave background radiation, the afterglow of the Big Bang, and observed that certain galaxy clusters moved towards a specific part of the sky. This motion seemed beyond what could be explained by gravitational influences from known structures such as superclusters or filamentary networks of galaxies within the observable universe. The existence of dark flow suggests influences beyond the observable universe causing these motions. It raises questions about the limits of our current cosmological models and potentially hints at structures or effects outside our cosmic horizon, the furthest distance from which light has had time to reach us since the beginning of the universe. Some scientists speculate that this could imply the presence of massive structures or even other universes whose gravitational pull affects our observable universe. This enigmatic movement challenges our understanding because it pushes the boundaries of known physics and forces us to consider that the cosmos might be even more vast and complex than we currently comprehend. Exploring this further could lead to groundbreaking insights about the universe's fabric, its origins, and the potential existence of multiversal realms. Addressing these mysteries drives cosmology to think boldly, expanding our comprehension of everything that lies beyond our cosmic line of sight. Hypernovae are extraordinarily powerful stellar explosions, far more energetic than typical supernovae. They result from the collapse of massive stars, generally at least 30 times the mass of our Sun. When such a colossal star exhausts its nuclear fuel, its core collapses under gravity's immense force, leading to a cataclysmic release of energy. A primary characteristic distinguishing hypernovae from regular supernovae is their immense energy output. While supernovae release an astounding amount of energy, hypernovae can be 10 to 100 times more powerful. The underlying mechanisms for this heightened energy relate to the star's mass and the nature of its collapse. In a hypernova, the core collapse may result in the formation of a black hole rather than a neutron star, as is common in many supernovae. Hypernovae also exhibit unique features in their emissions. For instance, they are often associated with long-duration gamma-ray bursts, some of the brightest electromagnetic events in the universe. These bursts are thought to arise from jets of particles moving at nearly the speed of light emanating from the star's poles as it collapses into a black hole. This jet formation requires very specific conditions typically found in the most massive stars with rapid rotation. Another difference is their impact on the cosmos. Hypernovae play a crucial role in seeding the universe with heavy elements. During these colossal explosions, elements heavier than iron are forged and dispersed into the surrounding space, aiding in the creation of future stars and planetary systems. While supernovae also contribute to this process, the sheer scale at which hypernovae do so is significantly greater, ensuring their indelible mark on the universe's evolutionary tapestry. Magnetars generate the most powerful magnetic fields in the universe through processes initiated during their birth from certain types of supernova explosions. When a massive star, typically around 10 to 25 times the mass of our Sun, exhausts its nuclear fuel, the resulting core collapse often forms a neutron star. However, if conditions during the collapse are just right, particularly involving the star's core rotation and magnetic alignment, a magnetar can be born. In a magnetar, the collapsing core's rapid spin and the intense compression of magnetic field lines significantly amplify the magnetic field strength. This amplification can be up to a quadrillion times stronger than Earth's magnetic field. The star's magnetic field lines are tightly wound as the core shrinks dramatically in size, concentrating the magnetic energy into a far smaller volume. The extreme density and pressure inside a magnetar also contribute to the intense magnetic fields. The particles within the core, primarily neutrons, align in such a way that their magnetic moments reinforce each other rather than canceling out as they do in less dense conditions. This collective alignment magnifies the overall magnetic effect across the neutron star. Magnetars are distinguished by their highly unstable magnetic fields, which can cause dramatic and violent effects on their surfaces. These magnetic instabilities lead to starquakes and the release of enormous bursts of X-rays and gamma rays. These bursts are so powerful that they can affect satellites and even Earth's atmosphere, despite happening thousands or even millions of light-years away. These cataclysmic energies and magnetic forces ensure that magnetars stand as some of the universe's most extraordinary and enigmatic objects. Fast radio bursts, FRBs, are brief, intense flashes of radio waves that originate from far beyond our galaxy. These bursts last only milliseconds, but release an immense amount of energy, comparable to what our Sun emits over several days. The mysterious nature of their origins has captivated astronomers since the first one was discovered in 2007. One leading hypothesis is that FRBs are caused by highly magnetized neutron stars known as magnetars. Magnetars possess incredibly powerful magnetic fields, and these fields can sometimes undergo sudden changes. These magnetostarquakes or other magnetic instabilities might produce the rapid bursts of energy that we detect as FRBs. Some FRBs have been traced back to regions in space where massive stars often end their lives, lending support to this theory. Another potential source of FRBs is the collision or merging of compact objects such as neutron stars or black holes. When these dense stellar remnants collide, they can create shock waves and potentially emit these powerful radio bursts. The rare nature of such collisions matches the observed scarcity and randomness of FRBs, making this a plausible explanation for at least some of the bursts. Interestingly, some FRBs repeat, providing further clues to their nature. The repeating nature suggests that the same source can produce multiple bursts over time, contrasting with cataclysmic events like collisions that happen only once. This observation has led to theories involving objects with continuous emissions, like rotating neutron stars in binary systems or interactions between a magnetar and its surrounding environment. While our understanding of FRBs is still evolving, each new discovery adds pieces to the complex puzzle of their origins. As we improve our detection abilities and gather more data, we hope to unravel the enigmatic nature of these extraordinary cosmic phenomena. Binary star systems consist of two stars orbiting a common center of mass, and their evolution and interaction can be profoundly different from that of solitary stars. The dynamics within these systems lead to unique behaviors and phenomena that are fascinating to astronomers. Initially, when both stars in a binary system are relatively young and still on the main sequence, they interact primarily through gravitational influence. Each star orbits the system's center of mass, a point determined by their respective masses. If the two stars are close, gravitational interactions can become quite complex. These interactions can cause changes in their orbits and in some cases result in mass transfer, where one star pulls material from its companion. As these stars age and exhaust their nuclear fuel, the more massive star typically becomes a red giant first. As it expands, its outer layers may overflow its Roche lobe, an imaginary teardrop-shaped region around each star where material is gravitationally bound to that star. When this occurs, material can transfer to the companion star. This mass transfer significantly alters the evolution of both stars, potentially spinning up the receiving star and affecting its stellar life cycle. In some cases, this mass transfer can lead to dramatic phenomena. For instance, if the donor star sheds its outer layers rapidly enough, it might become a white dwarf. The accreting star might gain enough mass to experience increased nuclear activity or even explode as a supernova if it surpasses critical mass thresholds. Additionally, if the stars in the binary system are close enough, they might eventually merge, leading to further stellar cataclysms and potentially forming a new single massive star or a neutron star. Binary interactions can also lead to the production of exotic objects such as X-ray binaries or millisecond pulsars. In X-ray binaries, the compact remnant of one star, such as a neutron star or a black hole, accretes matter from a companion star, emitting intense X-rays. Millisecond pulsars, on the other hand, are neutron stars that have been spun up by accreting material from a companion, rotating hundreds of times per second. Overall, the interplay between stars in binary systems showcases nature's complexity, leading to some of the most energetic and exotic phenomena in the universe, continually reshaping our understanding of stellar evolution and interaction. Quark stars are hypothetical celestial objects representing an extreme state of matter. They are thought to form under conditions even more extreme than those that create neutron stars. Essentially, a quark star would be formed if a neutron star's core density surpassed a critical threshold, causing neutrons to break down into their constituent particles known as quarks. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, often leaving behind a dense core. Typically, if the remaining core's mass is sufficient, it will collapse into a neutron star, where matter is compressed to a state where neutrons are densely packed together. However, if the mass and pressure exceed a certain limit, it is theorized that these neutrons could decompose into quarks, resulting in a quark star. These quark stars would be composed of quark matter, a substance theorized to be denser than neutronium, the matter found in neutron stars. There are two primary types of quarks thought to make up this ultra-dense matter: up quarks and down quarks, which constitute neutrons, along with possible strange quarks, creating what is sometimes referred to as strange matter. This state of matter is so compact that it would have a bizarre property. Any additional matter falling onto a quark star would be immediately integrated into the quark matter, contributing little to increasing the star's size. Observationally distinguishing quark stars from neutron stars poses a significant challenge, as both types of stars would exhibit similar characteristics. However, if quark stars exist, they might display slightly different mass and size relationships, known as mass-radius relationships, compared to neutron stars. They may also exhibit unique cooling patterns or emit bursts of energy detectable by astronomical instruments. The existence of quark stars remains hypothetical, yet the concept pushes the boundaries of our understanding of particle physics and stellar evolution. Confirming the existence of quark stars would not only provide insights into the behavior of matter under extreme conditions, but also deepen our grasp of the fundamental forces shaping the universe. Evidence for the existence of dark matter is drawn from various astronomical observations that reveal discrepancies between the predicted and observed behavior of cosmic structures. One of the earliest and most compelling pieces of evidence comes from the study of galaxy rotation curves. When astronomers, including Vera Rubin in the 1970s, measured the rotation speeds of stars in galaxies, they found that stars at the outer edges rotated just as quickly as those near the center. According to Newtonian mechanics, the stars further from the center should rotate more slowly unless there is additional unseen mass providing gravitational pull. This suggests the presence of an unseen or dark matter component. Another significant source of evidence comes from gravitational lensing, where light from distant galaxies is bent around massive objects like galaxy clusters. The degree of bending observed cannot be accounted for solely by the visible matter in these clusters. Instead, it indicates that there is much more mass present, exerting the gravitational forces necessary to curve the light to the extent observed. The cosmic microwave background radiation, the afterglow of the Big Bang, also provides clues. Measurements taken by satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft reveal subtle temperature fluctuations in this ancient radiation. By analyzing these fluctuations and the distribution of galaxies in the universe, cosmologists can infer the total amount of matter and energy. The results indicate that only about 1/6 of this matter is the regular baryonic matter we can see, and interact with the rest is dark matter. Finally, observations of galaxy cluster movements offer additional evidence. One famous example is the Bullet Cluster, where two galaxy clusters collided. The collision separated the dark matter from the normal matter, producing distinct gravitational effects observable through gravitational lensing. The visible matter, predominantly gas, slowed down and collided, whereas the dark matter continued largely unimpeded. This separation provided a clear picture of dark matter's presence and its different physical properties compared to normal matter. All these observations collectively build a strong case for dark matter's existence. Despite being invisible and not interacting with electromagnetic forces, dark matter's gravitational influence is critical in shaping the structure and evolution of the universe. Its detection remains one of the most exciting frontiers in modern astrophysics and cosmology, with experiments ongoing both in space and on Earth to directly detect dark matter particles. Dark energy is a mysterious and pervasive force believed to be responsible for the accelerating expansion of the universe. Discovered in the late 1990s through observations of distant type Ia supernovae, dark energy is thought to make up about 2/3 of the total energy density of the universe. Its properties and behavior remain among the biggest questions in cosmology. One way to conceptualize dark energy is through a term in Einstein's equations of general relativity known as the cosmological constant, often symbolized by the Greek letter lambda. This constant can be thought of as an inherent energy of empty space, which exerts a repulsive force counteracting the gravitational pull of matter. As the universe expands, more space is created, and with it more dark energy. This amplifies the repulsive effect, leading to an accelerating expansion. Another perspective is that dark energy could be a dynamic field similar to, but distinct from, gravity, dubbed quintessence. Unlike the static energy of the cosmological constant, quintessence would evolve over time, changing the rate at which the universe expands. This viewpoint allows for more complex models and could potentially explain the observed variations in the acceleration rate more flexibly. Dark energy-S effects are not immediately noticeable on small scales, such as within galaxies or even galaxy clusters where gravitational forces dominate. However, on the cosmic scale, its influence becomes profound. The accelerated expansion was confirmed through various means, including the study of the cosmic microwave background radiation and large-scale galaxy surveys, which show that galaxies are moving away from each other more rapidly over time. Current and future observational projects like the Euclid satellite mission and the Vera C. Rubin Observatory aim to map the distribution of galaxies and measure the expansion rate of the universe with unprecedented precision. By examining the large-scale structure of the cosmos and the behavior of dark energy over time, scientists hope to uncover its nature, potentially leading to groundbreaking discoveries that could reshape our understanding of physics and the universe. The intriguing possibility that dark matter might be composed of primordial black holes has garnered considerable interest among scientists. Primordial black holes are hypothetical objects that could have formed in the very early universe shortly after the Big Bang due to high-density fluctuations. Unlike typical black holes, which form from the collapse of massive stars, primordial black holes could be much smaller and represent an entirely different origin of dark matter. One point in favor of this hypothesis is that primordial black holes naturally exhibit many characteristics expected of dark matter. They are massive and do not emit light, fitting the profile of the elusive dark matter that influences the gravitational dynamics of galaxies and galaxy clusters. However, several constraints challenge this theory. Observations of gravitational lensing, where light from distant stars and galaxies is bent by a massive object, have not detected the expected number of lensing events that primordial black holes would cause if they were present in sufficient quantities to account for all dark matter. This places a significant limitation on their possible abundance and distribution. Additionally, primordial black holes of intermediate mass ranges might emit detectable levels of Hawking radiation or could lead to specific observable effects, such as interactions with stars and gas clouds, which we have not witnessed. Constraints from cosmic microwave background radiation also indicate that the contribution of primordial black holes to the total dark matter content must be small. Despite these challenges, the idea has not been entirely ruled out. Recent developments in astrophysics and gravitational wave astronomy, particularly those from the LIGO and Virgo collaborations detecting mergers of black holes, have revived interest in the possibility of primordial black holes. Some of these mergers involve black holes of masses and frequencies that might be consistent with primordial origins. Ongoing and future observational efforts aim to explore various mass ranges and properties of primordial black holes more comprehensively. While we continue to seek direct evidence for dark matter particles and alternative explanations, the primordial black hole hypothesis remains an intriguing possibility that could, if proven, offer revolutionary insights into both dark matter and the formation of the early universe. Weakly interacting massive particles. WIMPs are among the leading candidates to explain the elusive nature of dark matter. These hypothetical particles are thought to have significant mass and interact only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. The concept of WIMPs emerges naturally from extensions to the standard model of particle physics, such as supersymmetry, which posits the existence of heavier counterparts to known particles. One of these potential particles could be a WIMP, possessing the right properties to account for the observed effects of dark matter on the cosmic scale. One key reason WIMPs are considered viable dark matter candidates is the so-called WIMP miracle. When scientists calculate how WIMPs would have behaved in the early universe, they find that particles with the right mass and weak interaction properties would have naturally resulted in an abundance consistent with the observed density of dark matter today. This elegant coincidence strengthens the case for WIMPs as dark matter constituents. Detecting WIMPs directly involves several experimental approaches. Direct detection experiments, such as those conducted with large underground detectors filled with supercooled noble gases like xenon or argon, aim to spot the rare interactions between WIMPs and atomic nuclei. These interactions would produce tiny signals of light or heat, which researchers analyze to determine if they match the expected profile of WIMP interactions. Indirect detection methods focus on looking for the byproducts of WIMP annihilations or decays. If WIMPs exist, they could occasionally collide and annihilate each other, producing detectable particles like gamma rays, neutrinos, or other standard particles. These signals could be observed by space-based or ground-based telescopes. Another approach involves searching for anomalies in cosmic radiation that could hint at WIMP interactions. When particles collide, they might annihilate each other and produce gamma rays, neutrinos, or other particles detectable by instruments like the Fermi Gamma Ray Space Telescope. Particle accelerators, such as the Large Hadron Collider, seek to create WIMPs by colliding protons at extremely high energies. Scientists examine the debris from these collisions to spot missing energy or momentum signatures indicative of WIMPs. While WIMPs remain undetected, ongoing research and technological advancements push the boundaries, offering hope for eventual identification. Confirming WIMPs' existence would solve the dark matter mystery and potentially reveal new fundamental aspects of particle physics and the universe's fabric. Scientists use sophisticated techniques to detect dark matter particles directly, leveraging both underground detectors and advanced astronomical observatories. Although dark matter doesn't interact with light and remains invisible to traditional telescopes, it is theorized to interact via gravity and potentially the weak nuclear force. One primary method involves large underground detectors designed to identify interactions between dark matter particles and atomic nuclei. These detectors, located deep underground to shield from cosmic rays and background radiation, use noble gases like xenon or argon kept in a liquid state at ultra-low temperatures. When a dark matter particle interacts with the nucleus of an atom within the detector, it produces tiny flashes of light or minute amounts of heat. Despite the infrequency of these interactions, ultra-sensitive photodetectors and thermal sensors capture these rare events. Experiments such as Xenon in Italy and Lux Zeppelin in the United States exemplify this approach, employing enormous tanks of liquid xenon monitored for potential interactions. Another technique focuses on indirect detection methods, looking for byproducts of dark matter interactions in space, such as gamma rays, neutrinos, or electron-positron pairs that could be generated if dark matter particles annihilate each other or decay. Instruments like the Fermi Gamma Ray Space Telescope observe regions like galaxy centers, where dark matter density is high, searching for unexpected particle excesses. Particle accelerators offer another avenue for potential dark matter detection. By smashing protons together at extremely high energies, as done at the Large Hadron Collider in Switzerland, physicists attempt to recreate conditions similar to those following the Big Bang. The goal is to produce dark matter particles inferred from missing energy and momentum in collision events. This indirect signature suggests the creation of particles that do not interact like those in the Standard Model, potentially indicating dark matter. Hence, scientists employ an array of cutting-edge technologies and methodologies, pushing detection boundaries. While direct evidence of dark matter remains elusive, these innovative and complementary approaches significantly narrow down the possibilities, bringing us closer to uncovering one of the universe's greatest mysteries. Ultra-high-energy cosmic rays are particles, primarily protons or heavier atomic nuclei, that travel through space at nearly the speed of light and possess energy far exceeding typical cosmic rays. These particles can have energies millions of times greater than those produced in man-made particle accelerators, making them some of the most energetic particles in the universe. The precise origins of ultra-high-energy cosmic rays remain one of the great mysteries in astrophysics. However, several potential sources are thought to be responsible for their extraordinary energies. One hypothesis involves active galactic nuclei, which are supermassive black holes at the centers of distant galaxies. These AGNs are surrounded by vast accretion disks of gas and dust, which, when falling into the black hole, can get accelerated to incredible speeds, generating powerful jets capable of propelling particles to extreme energies. Another potential source could be gamma-ray bursts, among the most energetic events observed in the universe. These bursts occur when massive stars collapse into black holes or when binary neutron stars collide. The intense explosion releases enormous amounts of energy in a short time, potentially accelerating particles to ultra-high energies. Supernova remnants within our galaxy are also considered potential contributors, particularly those involving very massive stars. The shock waves generated by supernova explosions can accelerate particles to high energies through a process known as Fermi acceleration. While supernovae are well-established sources of lower-energy cosmic rays, it is possible that, under the right conditions, they could also produce ultra-high-energy cosmic rays. Additionally, interactions between cosmic rays and interstellar or intergalactic magnetic fields can also play a role in accelerating particles. These magnetic fields can bend and twist particle trajectories, amplifying their energies over vast distances through a process known as diffusive shock acceleration. Detecting and studying ultra-high-energy cosmic rays involve ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array project in Utah. These observatories use extensive arrays of detectors spread over large areas to capture and analyze the secondary particle showers produced when ultra-high-energy cosmic rays collide with molecules in Earth's atmosphere. By studying the patterns, isotopes, and energy spectra of these cosmic ray impacts, scientists hope to unravel the origins and acceleration mechanisms of these extraordinarily energetic particles. As we gather more data, the secrets of ultra-high-energy cosmic rays slowly reveal themselves, potentially offering new insights into some of the most violent processes in the cosmos. Cosmic ray air showers occur when high-energy cosmic rays, primarily composed of protons or heavier nuclei, enter Earth's atmosphere and collide with atmospheric particles. This collision initiates a cascade of secondary particles that spread out in an extensive shower, which scientists can detect and study using ground-based observatories. When a primary cosmic ray traveling nearly at the speed of light strikes a molecule in the upper atmosphere, it initiates a high-energy collision, producing a variety of secondary particles. These first-generation particles typically include pions, kaons, and other hadrons. The process is highly energetic, with the initial impact often resulting in the creation of hundreds or even thousands of secondary particles. As these secondary particles travel further into the atmosphere, they collide with additional molecules, generating even more particles. The shower grows exponentially, creating a complex web of interactions. During this cascade, pions and kaons quickly decay into lighter particles like muons, electrons, neutrinos, and photons. Photon interactions can lead to pair production, where a photon converts into an electron and its antimatter counterpart, the positron. Similarly, electrons and positrons can emit photons through a process called Bremsstrahlung, feeding back into the cascade and producing more particles. This chain reaction results in a broad shower of secondary particles that spreads wider as it propagates through the atmosphere. The composition of the secondary particles changes as the shower progresses. At lower altitudes, the shower predominantly consists of photons, electrons, and muons, as many of the hadrons have decayed or lost energy through interactions. Muons, being relatively stable and less interactive, can penetrate deep into the atmosphere, sometimes even reaching the ground where they can be detected by sensitive instruments. Water Cherenkov tanks detect the Cherenkov radiation emitted when muons and electrons move through the water faster than the speed of light in that medium, creating a distinctive blue glow. Scintillators detect charged particles through the light produced when particles pass through specific materials. By analyzing the pattern, timing, and intensity of the detected particles, scientists can reconstruct the properties of the original cosmic ray, including its energy, arrival direction, and potentially its source. This information helps in understanding cosmic ray origins and the fundamental processes that govern high-energy particle interactions in the universe. The Oh My God particle refers to an ultra-high-energy cosmic ray detected on the evening of October 15, 1991, by the Fly-SI cosmic ray detector in Utah. It astonished scientists because it possessed an energy of roughly 300 million electron volts, a level far beyond what had ever been observed before, and millions of times greater than particles encountered in man-made particle accelerators. What made the Oh My God particle particularly surprising was its sheer energy, which challenged our understanding of how the universe can accelerate particles to such extreme levels. To put this into perspective, The kinetic energy of this single proton was roughly equivalent to that of a baseball traveling at substantial speed around 90 kilometers AH. Such energy levels are extraordinarily difficult to achieve, considering the known mechanisms of particle acceleration in astrophysical environments. The detection of the "Oh my God" particle raised numerous questions about the potential sources of such high-energy cosmic rays. Conventional astrophysical objects, such as supernova remnants or even active galactic nuclei, typically cannot account for the extraordinary energies observed. Some scientists speculated that exotic and rare astrophysical events, like colliding neutron stars, supermassive black hole jets, or even processes related to the early universe just after the Big Bang, might be responsible. Additionally, the "Oh my God" particle also posed a puzzle related to the GZK limit, Greisen-Zatsepin-Kuzmin limit, a theoretical upper bound on the energy of cosmic rays. According to this limit, cosmic rays with energies above roughly 5 million electron volts should interact with the cosmic microwave background radiation, losing energy over vast distances. Therefore, observations of such high-energy particles suggest that they either originate from relatively nearby extragalactic sources or that some unknown mechanism allows them to preserve their energy over greater distances than currently understood. Since the detection of the "Oh my God" particle, several other ultra-high-energy cosmic rays have been observed, but the original discovery remains a landmark event in astroparticle physics. These detections continue to spur research and debate about the processes capable of producing such phenomenal energies, pushing the boundaries of our understanding of the most energetic phenomena in the universe. Cosmic rays pose significant challenges and risks for space travel and the health of astronauts. These high-energy particles, originating from the Sun, distant stars, and other cosmic sources, can have profound effects on both spacecraft and the human body. One primary concern is the health risk from prolonged exposure to cosmic rays. Unlike Earth's surface, which benefits from the planet's magnetic field and atmosphere acting as protective shields, space lacks such defenses. Consequently, astronauts are directly exposed to these high-energy particles, which can penetrate human tissue and even spacecraft material. The radiation can cause various biological effects, including DNA and cellular structure damage, increasing the risk of cancer, cataracts, neurological disorders, and other health issues. The longer the mission, such as a journey to Mars, the greater the cumulative exposure and associated risks. Beyond individual health, cosmic rays can also impact spacecraft electronics through a phenomenon called single-event effects. When high-energy particles strike electronic components, they can induce errors, disrupt operations, or permanently damage critical systems. Ensuring the reliability of spacecraft and its instruments in the face of such potential disruptions is vital for mission planning and engineering. To mitigate these risks, several strategies are employed. Spacecraft are designed with shielding materials to reduce astronauts and sensitive electronics exposure to cosmic rays. Although complete protection is impossible without impractically heavy shields, materials like polyethylene and water offer some degree of attenuation. Additionally, spacecraft trajectories and mission durations are carefully planned to minimize exposure during periods of heightened solar activity, such as solar flares, which can significantly elevate the already considerable levels of radiation in space. For astronaut health, space agencies are also exploring the development of pharmaceuticals and other medical countermeasures that might help mitigate the effects of radiation exposure. Continuous monitoring of radiation levels using onboard sensors provides real-time data to assess and respond to elevated risks during the mission. In conclusion, cosmic rays present a formidable challenge for space exploration. Through advanced engineering, prudent mission planning, and ongoing research into protective measures, the goal is to safeguard astronauts as humanity pushes further into the cosmos. The broader understanding and mitigation of these effects are essential to the success and health of future long-duration space missions. Neutrino detectors are remarkable instruments that allow scientists to peer into the heart of some of the universe's most dramatic events. Unlike photons or charged particles, neutrinos barely interact with matter, making them incredibly challenging to detect but simultaneously perfect messengers from the extreme environments where they originate. For instance, they can travel directly from supernova or the depths of the sun without being deflected or absorbed, carrying crucial information about those sources. By catching these elusive particles, neutrino detectors help us understand processes like nuclear fusion inside stars. The sun, powered by such fusion reactions, emits a constant stream of neutrinos. Studying them gives us direct evidence of the sun's inner workings, validating models of stellar physics. Similarly, detecting neutrinos from supernovae helps scientists investigate the explosive deaths of massive stars, shedding light on the production of heavy elements in the universe and the birth of neutron stars or black holes. Neutrinos also offer insights into the most fundamental aspects of physics. For instance, their ability to change from one type to another, a phenomenon known as neutrino oscillation, has provided compelling evidence that they indeed have mass, contrary to earlier assumptions. This discovery has profound implications for our understanding of particle physics and the fundamental forces governing the universe. Furthermore, exploring neutrinos from extragalactic sources opens up a new window into high-energy astrophysics. These particles might originate from active galactic nuclei or other mysterious cosmic phenomena, giving researchers clues about the most energetic processes in the cosmos. By studying neutrinos, scientists obtain a unique and otherwise unreachable perspective on both the most distant and the most hidden corners of the universe. Time dilation is a fascinating consequence of Einstein's theories of relativity and plays a crucial role in the functionality of Global Positioning System (GPS) satellites. These satellites orbit the Earth at high speeds and at different altitudes compared to the planet's surface. According to general relativity, time runs slower in stronger gravitational fields, meaning clocks on Earth's surface tick slightly slower than those further away in space. Meanwhile, special relativity predicts that due to their high velocities, time on board the satellites also runs slightly slower compared to a stationary observer on Earth. For the GPS to work accurately, the clocks on these satellites must synchronize precisely with clocks on Earth. Without adjusting for time dilation, even a tiny discrepancy can result in significant errors in position calculations. Specifically, the combined effects of special and general relativity mean that the satellite clocks tick faster than those on Earth by about 38 microseconds per day. While this might seem minuscule, over time it would lead to significant errors in position measurements errors as large as 10 kilometers per day. To counteract this, the clocks on GPS satellites are preset to tick slightly slower before launch, ensuring that when they reach orbit, they match the pace of Earth's clocks. Additionally, onboard computers continuously adjust the satellite time to account for any relative motion and gravitational differences. Ensuring this level of precision is essential for the myriad applications that rely on the GPS, from navigation and mapping services to synchronizing telecommunications and even aiding in financial transactions. Time dilation adjustments thus embody the elegant interplay between theoretical physics and practical technology, underscoring how our understanding of the cosmos directly impacts everyday life. Gravitational waves are ripples in the fabric of space-time itself, caused by some of the most violent and energetic processes in the universe. Predicted by Albert Einstein's theory of general relativity, these waves travel at the speed of light and are generated when massive objects accelerate, especially in scenarios involving extreme gravitational fields. Examples include the merging of black holes or neutron stars, supernova explosions, and even the rapid rotation of massive stars. Detecting these elusive waves requires extremely sensitive instruments, as they cause space to stretch and compress by minuscule amounts. The most prominent tool for this task is the Laser Interferometer Gravitational Wave Observatory LIGO. LIGO consists of two L-shaped interferometers, one in Washington State and the other in Louisiana, each with arms that are kilometers long. A laser beam is split and sent down each arm. If a gravitational wave passes through, it changes the length of the arm slightly, altering the time it takes for the laser beams to return and recombine. When the beams return and recombine, any difference in length causes an interference pattern, which can be measured with astonishing sensitivity. In 2015, LIGO made the first direct detection of gravitational waves from a collision of two black holes, a discovery that confirmed a major prediction of general relativity and opened an entirely new way to observe the universe. This event marked the beginning of gravitational wave astronomy. With advancements in technology and additional detectors like Virgo in Italy and the upcoming Kagra in Japan, our ability to pinpoint the sources of these cosmic waves is improving. By studying gravitational waves, scientists aim to uncover details about objects and events previously hidden from our view, giving us a deeper understanding of the dynamics of the cosmos. Wormholes, theoretical passages through space-time, have long captured the imagination with the enticing possibility of faster-than-light travel. Based on solutions to Einstein's equations of general relativity, wormholes could provide shortcuts between distant points in the universe. Imagine a tunnel with two ends located in different parts of space and time. If such a tunnel existed, traversing it could potentially allow one to travel great distances instantaneously, bypassing the limitations of light speed. However, the concept of using wormholes for faster-than-light travel faces several significant hurdles. The first challenge is stability. Most solutions for wormholes suggest they would collapse almost instantly upon formation, preventing anything, even light, from passing through. To keep a wormhole open and traversable, some form of exotic matter with negative energy density would be required. Such matter would counteract the natural tendency of the wormhole to pinch off. But creating or sustaining this exotic matter is beyond our current technological and scientific capability. Even if we could stabilize a wormhole, there are questions about their traversability and safety. The intense gravitational forces near the throat of a wormhole could potentially stretch and compress anything trying to pass through it, a process often referred to as spaghettification. Furthermore, solutions involving wormholes sometimes imply the existence of causality paradoxes, like the possibility of time travel, which introduces a host of theoretical and practical complications. While wormholes remain a fascinating idea in theoretical physics and a staple of science fiction, actual evidence for their existence or our ability to use them for travel remains elusive. As of now, they are rich arenas for thought experiments and underline the profound complexities of space-time, but they are far from providing a practical solution for faster-than-light travel. Nonetheless, studying wormholes continues to push the boundaries of our understanding, challenging scientists to think beyond the limits of known physics. Frame dragging, also known as the lens-thirring effect, is a fascinating phenomenon that occurs near rotating massive objects. According to Einstein's theory of general relativity, mass and energy warp space-time, creating the gravitational effects we observe. However, when an object rotates, it does more than just warp space-time, it also drags it along with its rotation. Imagine space-time as a viscous fluid and a rotating object, like a star or black hole, as a stirrer. As the object spins, it twists the space-time around it. This effect is most pronounced near extremely massive and rapidly rotating bodies, such as neutron stars and black holes. The closer one gets to these objects, the stronger the frame dragging effect becomes. Detecting frame dragging is incredibly challenging because its effects are subtle and require sensitive instrumentation. One of the most compelling confirmations of this phenomenon came from NASA's Gravity Probe B mission, launched in 2004. The spacecraft carried ultra-precise gyroscopes intended to measure the tiny angle changes caused by Earth's rotation dragging space-time around it. After years of data analysis, the results confirmed the presence of frame dragging, albeit on a very small scale. Frame dragging has significant implications for our understanding of the cosmos. Around rotating black holes, for instance, this effect could influence the paths of particles and light, shaping the structure and dynamics of accretion disks and jets emitted by these enigmatic objects. By studying frame dragging, scientists not only test and refine our understanding of general relativity, but also gather crucial insights into the complex behaviors near some of the most extreme environments in the universe. The twin paradox is a thought experiment that vividly demonstrates time dilation, a concept rooted in Einstein's theory of special relativity. In this scenario, imagine two identical twins. One remains on Earth, while the other embarks on a journey through space at a velocity close to the speed of light. According to special relativity, the twin traveling at high speed experiences time more slowly compared to the twin who stays behind. Here is how the paradox unfolds. The traveling twin sets off on a journey to a distant star at near light speed and then returns to Earth. Upon reuniting with the Earthbound twin, the traveling twin finds less time has passed for them than for their sibling who remained on Earth. While the Earthbound twin may have aged, say, 10 years, the traveling twin might have aged only a fraction of that time, depending on the exact speed and duration of the journey. This discrepancy arises because, per special relativity, moving clocks run slower when observed from a stationary frame of reference. The term paradox emerges because it initially seems counterintuitive. One might wonder if each twin could consider the other as moving. Why wouldn't they both experience time dilation equally? The resolution lies in the fact that the traveling twin undergoes acceleration and deceleration during their journey, breaking the symmetry of the situation. This makes the traveling twin S frame of reference non-inertial, different from the stay-at-home twin S inertial frame. The twin paradox illustrates the real and measurable effects of relativity. Indeed, this effect is not just a theoretical curiosity, it has practical applications, such as in the functioning of GPS satellites, where time dilation must be accounted for to maintain the accuracy of navigation signals. Thus, the twin paradox offers a compelling glimpse into the strange and counterintuitive nature of time in our relativistic universe. The mysterious gamma-ray glow at the center of our galaxy, often referred to as the Galactic Center GeV excess, has puzzled astronomers since its discovery. These high-energy gamma rays, detected by telescopes like the Fermi Gamma Ray Space Telescope, seem to emanate from an area densely packed with stars, dust, and energetic phenomena. The exact source of this gamma-ray emission is still under investigation, and several compelling theories have been proposed. One significant hypothesis suggests that dark matter particles might be annihilating each other in the dense region of the galactic center. Dark matter, which makes up a substantial portion of the universe's mass, remains largely undetectable except through its gravitational effects. If dark matter particles occasionally collide and annihilate, they could produce high-energy gamma rays as a byproduct. This would be a groundbreaking discovery, shedding light on the elusive nature of dark matter. Another theory attributes the gamma-ray excess to a population of millisecond pulsars, which are rapidly rotating neutron stars that emit beams of radiation, including gamma rays. They are thought to be numerous in the crowded central regions of our galaxy. If these millisecond pulsars are indeed the source, it would mean that our understanding of the stellar population and high-energy processes in the inner galactic core needs significant adjustment. Alternatively, the gamma-ray glow could result from interactions between cosmic rays and the dense gas clouds in the galactic center. Cosmic rays, which are high-energy particles traveling through space, can collide with gas atoms, producing gamma rays in the process. Given the complex environment of the galactic center, with its intense magnetic fields and high stellar density, interactions of cosmic rays with this dense interstellar medium might be a plausible explanation for the observed gamma-ray excess. Such interactions can plausibly explain the observed gamma-ray excess. As scientists continue to explore these possibilities, each potential explanation offers a fascinating glimpse into the dynamic and energetic processes at play in our galaxy's core. Understanding the true source of this gamma-ray glow not only unravels a cosmic mystery, but also enhances our knowledge of the fundamental forces and particles that shape the universe. Supermassive stars like R136A1, found in the dense star cluster R136 in the Large Magellanic Cloud, represent some of the most extreme cosmic phenomena. Forming such enormous stars, which can have masses hundreds of times that of our Sun, requires specific and exceptional conditions that are still a subject of intense study and debate among astronomers. The formation process begins within giant molecular clouds, vast regions of cold gas and dust where stars are born. For a supermassive star to form, a particularly dense region within one of these clouds must collapse under its own gravity. The key to generating a star as massive as R13601 lies in the accumulation of an enormous amount of material from the surrounding cloud. This might happen in regions where star formation is particularly vigorous and the molecular cloud has unusually high mass and density. Once the progenitor gas cloud collapses, it forms a protostar that rapidly accretes more and more material. In environments like the R136 star cluster, neighboring stars and intense radiation can drive the accretion process, not only feeding the growing protostar, but also helping to clear away excess gas that might otherwise limit its growth. Despite these aiding factors, maintaining stability is a challenge because the massive star's intense radiation pressure can counteract gravity and hinder further growth. As these supermassive stars evolve, they burn through their nuclear fuel at an incredibly rapid rate. Their cores reach extreme temperatures and pressures, allowing for the fusion of heavier elements. However, this accelerated fusion process means that their lifespans are astonishingly brief, typically just a few million years compared to the billions of years for lower-mass stars like our Sun. Towards the end of their life cycle, supermassive stars undergo dramatic transformations, exploding as supernova or even hypernovae, releasing vast amounts of energy and enriching the interstellar medium with heavy elements. In some cases, they leave behind a dense core that collapses into a black hole. Through these cataclysmic ends, supermassive stars play a crucial role in the cosmic cycle of matter and the evolution of galaxies. Each stage of their life cycle offers invaluable insights into the extreme conditions and processes that shape the universe. High-velocity clouds are enigmatic, fast-moving clouds of gas that zip through the halo of the Milky Way at speeds reaching hundreds of kilometers per second relative to the galaxy's rotation. Their origins are varied and complex, pointing to multiple potential sources and mechanisms that contribute to their formation. One leading hypothesis suggests that some of these high-velocity clouds are remnants of the galactic fountain process. In this scenario, supernova explosions within the Milky Way's disk propel gas outward into the halo. This gas then cools, condenses, and eventually falls back toward the galactic plane. During its return journey, this recycled material can appear as high-velocity clouds, essentially rejuvenating the galaxy with newly cooled gas that contributes to future star formation. Another plausible source for high-velocity clouds is the interaction between the Milky Way and its satellite galaxies. As smaller galaxies like the Magellanic Clouds orbit and occasionally pass through the Milky Way's halo, their gravitational interactions and tidal forces can strip gas from these satellites. This stripped gas can then manifest as high-velocity clouds. Observations suggest that the Magellanic Stream, a long tail of gas trailing from the Magellanic Clouds, may significantly contribute to these high-velocity phenomena. Furthermore, some high-velocity clouds could be primordial gas left over from the formation of the Milky Way itself. These clouds might consist of relatively unprocessed material, representing the remains of the gas reservoir from the early universe that settled into the galaxy's halo. Studying these clouds can offer invaluable clues about the conditions of the early universe and the processes of galaxy formation and evolution. Regardless of their origins, high-velocity clouds play a crucial role in our understanding of galactic dynamics and the ongoing processes that shape the Milky Way. By observing and analyzing these swift gas clouds, astronomers uncover layers of complexity in our galaxy's history, interactions, and the continuous cycle of matter within the galactic environment. When galaxies collide and merge, these awe-inspiring cosmic events unfold over millions to billions of years, transforming the structures and dynamics of the galaxies involved. The process begins as galaxies, under the influence of mutual gravitational attraction, draw closer to each other. Contrary to the typical notion of violent impacts, individual stars within galaxies rarely collide due to the vast distances separating them. Instead, the interactions primarily involve the gravitational forces exerted on the stars, gas, and dark matter within the galaxies. As galaxies approach each other, their gravitational fields create tidal forces that distort their shapes. Spiral arms may become elongated or twisted, and streams of stars and gas can be flung out into intergalactic space. During these close encounters, the gas within the galaxies can experience intense compression, leading to bursts of star formation. Astronomers call these episodes starbursts, which can produce new stars at rates much higher than usual. Eventually, the galaxies pass through each other, but gravity pulls them back together, causing them to engage in several additional encounters and passes. These interactions dissipate their relative kinetic energy, causing them to coalesce into a single larger galaxy. Over time, the merging process leads to the mixing and settling of the various components. The initially chaotic motions of stars smooth out, often transforming the progenitor's morphologies. For instance, the merger of two spiral galaxies typically results in an elliptical galaxy characterized by random stellar orbits and a more spheroidal shape. Galactic mergers are fundamental processes in the hierarchical model of cosmic structure formation. They are instrumental in forming larger galaxies from smaller ones, a process known as hierarchical clustering. The evidence of past mergers is abundant in observations of galaxies, highlighting their importance in the evolution of cosmic structures. These interactions could explain the observed gamma-ray excess. As scientists delve deeper into these possibilities, each potential explanation provides fascinating insights into the dynamic and energetic processes occurring in our galaxy's core. Determining the true source of this gamma-ray glow not only unravels a cosmic mystery, but also enhances our understanding of the fundamental forces and particles shaping the universe. Supermassive stars like R136a1, located in the dense star cluster R136 in the Large Magellanic Cloud, are among the most extreme cosmic phenomena. Forming such enormous stars, which can have masses hundreds of times that of our Sun, requires specific and exceptional conditions, still a subject of intense study and debate among astronomers. The formation process begins within giant molecular clouds, vast regions of cold gas and dust where stars are born. For a supermassive star to form, a particularly dense region within one of these clouds must collapse under its gravity. The key to forming a star as massive as R136a1 lies in the accumulation of an enormous amount of material from the surrounding cloud. This might occur in regions where star formation is particularly vigorous and the molecular cloud has unusually high mass and density. Once the progenitor gas cloud collapses, it forms a protostar that rapidly accretes more and more material. In environments like the R136 star cluster, neighboring stars and intense radiation can drive the accretion process, feeding the growing protostar and helping to clear away excess gas that might otherwise limit its growth. Despite these aiding factors, maintaining stability is challenging because the massive star's intense radiation pressure can counteract gravity and hinder further growth. As these supermassive stars evolve, they burn through their nuclear fuel at an incredibly rapid rate. Their cores reach extreme temperatures and pressures, allowing for the fusion of heavier elements. However, this accelerated fusion process means their lifespans are astonishingly brief, typically just a few million years compared to the billions of years for lower-mass stars like our Sun. Towards the end of their life cycle, supermassive stars undergo dramatic transformations, exploding as supernovae or even hypernovae, releasing vast amounts of energy and enriching the interstellar medium with heavy elements. In some cases, they leave behind a dense core that collapses into a black hole. Through these cataclysmic ends, supermassive stars play a crucial role in the cosmic cycle of matter and the evolution of galaxies. Each stage of their life cycle offers invaluable insights into the extreme conditions and processes that shape the universe. High-velocity clouds are mysterious, fast-moving gas clouds that zip through the halo of the Milky Way at speeds reaching hundreds of kilometers per second relative to the galaxy's rotation. Their origins are varied and complex, pointing to multiple potential sources and mechanisms contributing to their formation. One leading hypothesis suggests that some of these high-velocity clouds are remnants of the galactic fountain process. In this scenario, supernova explosions within the Milky Way-S disk propel gas outward into the halo. This gas then cools, condenses, and eventually falls back toward the galactic plane. During its return journey, this recycled material can appear as high-velocity clouds, rejuvenating the galaxy with newly cooled gas that contributes to future star formation. Another plausible source for high-velocity clouds is the interaction between the Milky Way and its satellite galaxies. As smaller galaxies like the Magellanic Clouds orbit and occasionally pass through the Milky Way-S halo, their gravitational interactions and tidal forces can strip gas from these satellites. This stripped gas can then manifest as high-velocity clouds. Observations suggest that the Magellanic Stream, a long tail of gas trailing from the Magellanic Clouds, may significantly contribute to these high-velocity phenomena. Furthermore, some high-velocity clouds could be primordial gas left over from the formation of the Milky Way itself. These clouds might consist of relatively unprocessed material, representing the remains of the gas reservoir from the early universe that settled into the galaxy's S halo. Studying these clouds can offer invaluable clues about the conditions of the early universe and the processes of galaxy formation and evolution. Regardless of their origins, high-velocity clouds play a crucial role in our understanding of galactic dynamics and the ongoing processes that shape the Milky Way. By observing and analyzing these swift gas clouds, astronomers uncover layers of complexity in our galaxy's history, interactions, and the continuous cycle of matter within the galactic environment. When galaxies collide and merge, these awe-inspiring cosmic events unfold over millions to billions of years, transforming the structures and dynamics of the galaxies involved. The process begins as galaxies, under the influence of mutual gravitational attraction, draw closer to each other. Contrary to the typical notion of violent impacts, individual stars within galaxies rarely collide due to the vast distances separating them. Instead, the interactions primarily involve the gravitational forces exerted on the stars, gas, and dark matter within the galaxies. As galaxies approach each other, their gravitational fields create tidal forces that distort their shapes. Spiral arms may become elongated or twisted, and streams of stars and gas can be flung out into intergalactic space. During these close encounters, the gas within the galaxies can experience intense compression, leading to bursts of star formation. Astronomers call these episodes starbursts, which can produce new stars at rates much higher than usual. Eventually, the galaxies pass through each other, but gravity pulls them back together, causing them to engage in several additional encounters and passes. These interactions dissipate their relative kinetic energy, causing them to coalesce into a single larger galaxy. Over time, the merging process leads to the mixing and settling of the various components. The initially chaotic motions of stars smooth out, often transforming the progenitors' morphologies. For instance, the merger of two spiral galaxies typically results in an elliptical galaxy characterized by random stellar orbits and a more spheroidal shape. Galactic mergers are fundamental processes in the hierarchical model of cosmic structure formation. They are instrumental in forming larger galaxies from smaller ones, a process known as hierarchical clustering. The evidence of past mergers is abundant in observations of galaxies, highlighting their importance in the evolution of cost-accurate atomic clocks, often hydrogen masers, are used to timestamp received signals down to the nanosecond. Data from each telescope is recorded and sent to a central processing facility called a correlator. The correlator meticulously aligns these signals by accounting for time differences based on the telescope's locations and movements. By combining the data, the correlator constructs interference patterns that astronomers use to generate high-resolution images. This process allows scientists to observe celestial objects with detail comparable to a single telescope the size of the maximum distance between the individual radio telescopes. VLBI's power lies in its exceptional angular resolution, enabling scientists to observe and measure phenomena in remarkable detail. This technique has been instrumental in numerous groundbreaking discoveries, such as imaging the event horizon of a black hole for the first time with the Event Horizon Telescope, a global VLBI network. It also aids in studying the dynamics of quasars, mapping the distribution of matter in galaxies, and understanding pulsars and other compact objects. By overcoming the limitations of individual radio telescopes, VLBI exemplifies human ingenuity in astronomical observation, providing unparalleled insights into the universe's most distant and enigmatic objects. This collaborative effort across continents, and sometimes including space-based antennas, showcases the power of synchronizing technology and precision for unlocking cosmic secrets. Neutrino detectors offer profound insights into the Sun's core where nuclear fusion occurs. Neutrinos are subatomic particles produced during nuclear reactions, such as those powering the Sun. Because neutrinos interact weakly with matter, they can escape the Sun's core and travel across space virtually unimpeded, carrying direct information about the core's conditions. Neutrino detectors on Earth, like Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, capture these elusive particles. When neutrinos interact with the detecting material, usually a large volume of water or heavy water, they produce faint flashes of light known as Cherenkov radiation. Sensitive instruments detect these flashes, allowing scientists to count neutrino interactions and measure their properties, such as energy and flavor. By analyzing the flux and characteristics of these solar neutrinos, scientists can test and validate models of solar fusion and energy production. The standard solar model predicts specific neutrino production rates and energy distributions for different fusion reactions in the Sun's core. Observing these neutrinos directly confirms our understanding of the nuclear reactions converting hydrogen into helium, the primary energy source for the Sun. One remarkable finding from neutrino detection experiments was the initial discrepancy between the predicted and observed neutrino flux, known as the solar neutrino problem. This discrepancy was resolved by discovering that neutrinos can oscillate between different flavors, electron, muon, and tau, as they travel from the Sun to Earth. This neutrino oscillation provided crucial evidence for neutrino mass, fundamentally altering our understanding of particle physics. Thus, neutrino detectors offer an invaluable window into the Sun's otherwise inaccessible core, confirming theoretical models of stellar energy production and contributing to broader physics discoveries. Adaptive optics systems sharpen our view of the cosmos by counteracting the blurring effects of Earth's atmosphere. When light from celestial objects travels through the atmosphere, it gets distorted by shifting air currents and varying temperatures, causing stars to twinkle and images from ground-based telescopes to appear fuzzy. Adaptive optics systems achieve clarity by using tiny flexible mirrors that adjust their shape in real time. These mirrors are controlled by computers that analyze the incoming light, detecting atmospheric distortions. By rapidly tweaking the mirrors, usually many times per second, the system cancels out the atmospheric turbulence, producing a much sharper image. The technology is akin to wearing glasses that constantly adjust to keep things in focus, allowing astronomers to observe distant stars, galaxies, and other celestial phenomena with sharpness once possible only from space-based telescopes. This has revolutionized ground-based astronomy, enabling us to probe the universe with unprecedented precision and uncover hidden details, advancing our understanding of the cosmos. Protecting Mars from Earth's microbes during exploration involves a meticulous process known as planetary protection. This discipline ensures that terrestrial life does not contaminate the Martian environment, preserving its natural state for scientific study and preventing any potential interference with the search for indigenous life. Spacecraft destined for Mars must undergo rigorous sterilization procedures. Every component is meticulously cleaned and, when feasible, sterilized using heat, radiation, or chemical treatments. The assembly of these spacecraft occurs in ultra-clean facilities, where air filtration systems and strict cleanliness protocols minimize microbial presence. Once assembled, the spacecraft often undergo additional sterilization steps. For instance, parts of the spacecraft might be subjected to dry heat microbial reduction, a technique involving elevated temperatures designed to kill microorganisms. These measures ensure that even the most resilient microbes are significantly reduced. Additionally, scientists monitor and catalog microbial burdens on spacecraft using sensitive detection techniques to assess contaminant levels. This attention to detail ensures that as humanity reaches out to Mars, we respect and preserve its pristine, potentially habitable environments, allowing for accurate and uncontaminated scientific discoveries. Asteroid mining presents formidable technical and logistical challenges. Firstly, the sheer distance and isolation of asteroids pose significant hurdles. Reaching these celestial bodies requires spacecraft capable of enduring long-duration missions through the harsh environment of space, navigating to a moving target many millions of miles away. Once an asteroid is reached, another challenge arises: extremely low gravity. Operating machinery in such an environment is unlike anything on Earth, requiring anchors or specialized thrusters to keep equipment in place. The machinery itself must function reliably in the vacuum of space, where extreme temperatures and radiation are persistent issues. There is also the question of material processing and transportation. Extracted resources must be processed in situ or transported back to Earth or another location. Developing systems that can efficiently and safely handle this, potentially automated and without constant human oversight, is daunting. Additionally, the energy requirements for these processes are substantial, necessitating advanced power solutions such as solar arrays or nuclear power sources. Lastly, significant legal and ethical considerations need addressing. The Outer Space Treaty of 1967, to which many countries are signatories, states that celestial bodies are not subject to national appropriation. This presents a gray area regarding proprietary rights and obligations for asteroid mining, necessitating international cooperation and new regulations to ensure fair and sustainable use of extraterrestrial resources. Terraforming Mars to make it habitable for humans involves immense scientific and engineering challenges. Firstly, altering the Martian atmosphere is essential. Mars has a thin atmosphere primarily composed of carbon dioxide with little to no oxygen. One idea is to release trapped gases from the planet's surface or polar ice caps to thicken the atmosphere, potentially using greenhouse gases like perfluorocarbons to initiate a runaway greenhouse effect. Next, creating liquid water on Mars' surface is crucial. Mars currently has water in the form of ice, mostly at the poles and beneath the surface. Melting this ice to create stable bodies of water involves significantly raising the planet's temperature. Once liquid water exists, it could support life and improve the feasibility of growing crops. However, preventing rapid refreezing and maintaining a stable water supply would be ongoing challenges. Another critical aspect is generating breathable oxygen. Methods for oxygen production include utilizing photosynthetic organisms such as algae or advanced technological processes like electrolysis of water. Once consistent oxygen production is established, humans could start creating enclosed habitats with a controlled atmosphere, gradually expanding as more oxygen is produced and stored. Lastly, protecting Mars from harmful solar and cosmic radiation is vital due to its lack of a magnetic field similar to Earth's. Large-scale engineering projects such as constructing magnetic shields or creating subterranean habitats could provide necessary protection. While these steps present incredible scientific and logistical challenges, the potential for transforming Mars into a habitable world ignites the imagination and drives forward our exploration of possibilities in space colonization. Long-duration space travel imposes significant psychological challenges on astronauts, stemming from isolation, confinement, and prolonged separation from Earth. The relentless solitude can be daunting as astronauts operate in a small, enclosed environment with limited social interaction, leading to feelings of loneliness and strained mental health. Confinement in a spaceship or space station means limited physical space and privacy, which can heighten stress levels. The lack of natural environments and routine activities that